So our next talk is Reference Capabilities for Concurrency and Scalability by, is it Elias or Elias?
I will answer to both.
Which do you prefer?
What is your mother called?
My mother calls me Elias. So it's the third one. So.
Okay, and I will let you introduce yourself.
Thank you very much. Yes, so my name is Elias. And for people who remember the old name of Splash, I am from Uppsala, which is also a bit fun. Yeah, and I like to preface this by saying that please ask questions if you have them, because I'm hoping to get some discussions out of this, and I have more material that I can go into if you don't have questions, and I have things that I can skip if you don't. So, yeah, keep coming. So, the first thing that sort of should pop out at you is that it says reference capabilities for. So you might ask, why aren't we at OCAP? Shouldn't we be talking about object capabilities? And I'm here to try to discuss the similarities and the differences between them. So my understanding of object capability is that it's an unforgeable reference to an object, and it carries with it some permission to perform one or more operations on such an object. And this unforgeability is the important part here, that the only way that you can cause effects on an object is if you were given that capability. Now on the other hand, a reference capability is an object capability, still unforgeable, but it also carries with it some permission to perform operations on the reference itself. So note here that it's operation on the reference, meaning this operation on the reference could be moving the reference or copying the reference or saving the reference to the heap, but it doesn't concern what we do with the object. That's part of the object capability part. So in this talk, I'll be talking about mainly how we've been using reference capabilities in order to achieve data race freedom in a concurrent or parallel system like this. And if there's time, I will go into how we did more low-level stuff, like reasoning about ownership transfer with a sort of a reference capability style of reasoning. But I'll focus mostly on the data race freedom part. So the way we attack this, so there's been a lot of talk about security and authority, and the way we attack it is sort of looking at parallel programs. And the way we think about it is that we know that aliasing, when there are multiple references to an object, may cause data races. And sort of the slide just says this, but this should really come as a warning label on all languages that contains parallelism. That says, warning, this aliasing may cause data races, so you need to be careful. Because in general we have these threads and they are sharing a bunch of objects, and while we're running they have these effects on the objects. And if we aren't careful, two threads are going to crash, and there's going to be what we call a data race, which is when two threads access the same object at the same time, and they both, at least one of them updates the thing, then we have a data race. And the tricky thing about this, we usually think of data races as something going boom, but really it just leaves this object in sort of a sickly shade of blue like this, and then some other core thread comes along and is confused by some inconsistent value that wasn't there before. So and that's why we want to prevent data races, because they are notoriously hard to track down and fix these kind of bugs. So, right, you can't have data races without aliasing. You need aliasing to have data races. So, but you may be thinking, hey, aliasing doesn't cause data races, it's the lack of mutual exclusion which causes data races. So if you want to listen to Charlton Heston here, then we should be focusing not on aliasing, but we should be focusing on mutual exclusion. And so this sort of mutual exclusion, and it's sort of related to the idea of object capabilities which give the authority to perform certain operations. But object capabilities only get us part of the way. So the object capability tells you something about what you can do with an object. You know that you can call the foo and the bar operation on this object, and that's what you know. But you don't know anything about what anyone else can do concurrently. On the other hand, with a reference capability, you have this implicit guarantee about what others can do, at least if you're following a strict reference capability model. So here, for example, we still allow the foo and the bar operations, but the only permitted operations on the reference itself, or the capability itself, is to move it. This means that you're not allowed to copy the reference. And if this capability was created at the same time as the object, we know that the only way that you could have been given this capability is if someone moved it to you, and by move I mean if I pass the reference to someone else, I have to give it up. I'm not going to touch it anymore. So this way we know that there couldn't be another reference in the system at the same time, because that reference would have been forged. It would have been it would have violated the permissions that was given to this thing.
So they can't copy it first and then move it.
Exactly, because copy is not in the set of allowed permissions.
So as you move it, it has to be a subset
A subset of.
capabilities or the same
Oh,
capability.
right, exactly. So this is the copying. This also copies the set, and or so moving or copying also copies both sets like this, or makes it a subset. That's true. So we explored this in a paper from 2016, where we developed a type system called Kappa. So in Kappa we have, just as in object capability, so capability grants access to some object, and I'm going to sort of use capability and reference capability interchangeably here. So ask if there is confusion. And as usual, so the type of the capability defines the interface to the object. What are the operations allowed on it? And importantly here, a capability in Kappa assumes exclusive access to the object. So if it has been given this capability and it's accessing it, then it's going to assume that no one else is going to be accessing it at the same time, at least not in a way that would be unsafe. So the kind of thread safety we're looking at is to avoid data races altogether. And then in Kappa we annotate how this thread safety is achieved by adding a mode to the capability. So a capability is a mode and a type, like this. And the mode is the thing that expresses the permissions, the reference permissions that the reference capability gives. So for example, we saw the linear thing in other systems that would be called unique, and we think of that as a reference capability that only has a move permission. You're not allowed to copy the thing. Similarly, you could have a local capability, meaning that here's something that you're allowed to copy, but you're not allowed to copy it to a different thread. So you're allowed to make local copies, but you're not allowed to share this across different threads. And this way you know that if you're accessing it, you are the only one. You were never allowed to pass it to another thread, so you must have been the one who created it. So when you're accessing it, no other thread can access it at the same time, so there can be no data races. We can have modes which are shareable, which may have references from different threads at the same time. So we could have read capabilities saying that you're allowed to create a shareable alias of this thing if you promise to forget all the mutable capabilities at the same time. So when you have a read reference, you know that the only way you could have gotten that is by removing all of the mutating capabilities, and therefore you know that any concurrent accesses to this thing is going to be a read, and read races are benign. You can have things protected by a lock, saying that here is a reference, and you're not allowed to dereference this thing unless you take a lock. And by taking a lock, you sort of get additional permissions to actually access the thing for the duration of the lock. And this way you know that there may be several threads racing to access this thing, but if there is a concurrent access, then one of them will be blocked because of the lock. Similarly, you could have a reference which is has an asynchronous interface. So we think of it as an actor, for example. So you're not allowed to dereference it, but you can pass it messages asynchronously, and then you know that any concurrent accesses will be synchronized within the message queue of the actor. So interestingly, these modes all guarantee mutual exclusion. So while you're accessing it, no other threads can access the same object at the same time. So an interesting thing that reference capabilities allows us to do is to reason about encapsulation. And you can have a mode which is saying you're allowed to copy this thing locally, but you're not allowed to copy it outside of a certain aggregate. This is the sort of thing that ownership types would get you. And ownership types would be able to express sort of more fine-grained details about this thing. In this system, we can say that if you have a subordinate thing within an object which is local or linear or locked or active, then it may never escape that object. So there can never be a reference that passes through this thing. And this turns out to be really useful and interesting. So we've implemented this in a language called Encore, which is an actor-based programming language. This means that we have actors which are communicating by passing messages, and then each message is handled sequentially like this. And what's nice about the actor model is that one can reason about each actor in isolation. You don't have to think about what the other actors might be doing at the same time. And in order for this to work in at least an imperative setting where there's mutable state, you need to have some guarantees that this private state is indeed private, and we can use the reference capabilities to enforce this and say that one actor cannot access the private data of another actor. They may share things that are, for example, protected by a lock, or things that are read-only, but this thing may not exist. So isolation is a very powerful property, and that is possible to express with reference capabilities. But if we remember old Heston, he says that we should be able to have this reference as long as we can ensure mutual exclusion. I mean, the aliasing in itself is not the problem. The problem is mutual exclusion. So this makes it the fact that we're tracking this, we're statically tracking the encapsulation properties means that it's simple to switch from isolation-based model to a delegating model. So we get something like where we have this reference and we're allowed to pass it a message, and actually this message is going to be forwarded to the owner of the thing, and the owner is then going to perform the same thing. So this is like E-style far references, only that the actor here doesn't have to be on a different machine. It could be on the same machine.
So in terms of your terminology and taxonomy, you would say that the E-VAT model, that the distinction between a near reference and an eventual reference is a reference capability distinction, because it's about what the references can do, but it's not a exclusion distinction, because it doesn't tell you about what the absence of other references are.
I think so. Then could you briefly say what the eventual reference is?
The eventual reference, I think, is what your async reference is.
Okay.
It only allows you to queue a message to be delivered later to a particular object, but you're queuing it in the VAT hosting the object, which is, I think, the same thing as your owning thread.
Yeah.
Okay.
Yeah, definitely.
Okay.
And so and these are things that are sort of you could do the same thing. You're allowed to do the same thing with the references, but with the references, but not with the objects themselves. That makes sense.
Mm-hmm. Right. Yeah.
And if we sort of zoom in on this and sort of look at what's going on, sort of on the reference capability level. So we have some local reference capability, which allows some operations foo bar, and the set of permitted operations on this reference is you can either copy something internally, you can copy it near, or you can copy it far. When you copy it near, you just get exactly the same thing back. And when you do a far copy, like so, you get you get an alias of this, but where the operations have changed. So the operations now look asynchronous. It looks like you're sending messages to this thing, but they will actually be forwarded to the owner of this And that's why it says active within quotation marks. It's not actually an active. So if you could think of this as asynchronous or eventual. Yeah?
So can the owner change after you've done this? So the forwarding has to kind of keep up to date with changes of ownership?
That's an interesting thing, and there's a paper in submission that is discussing this thing. But I'll go into it briefly. So it's a lot simpler if the owner of the reference is always the same, because then we don't have to. If we're accessing something which is local, we know that it's always ours. But the problem is that if we could pass this, if this thing could change owner, then we would have to make sure that there are no lingering aliases here. So we'd have to make sure that we've transferred all of the thing, all of the aliases. And this forces us to do make some additional dynamic checks to sort of see if I'm accessing one of these guys, I have to think, am I the owner? In that case, I can access it synchronously without problems. Otherwise, I'm going to forward a message to it. So sort of the runtime cost increases a little bit, but it's possible. A bit simpler if we don't do it. And another interesting thing here is that we can take it a bit further, because this sort of gives us a way of safely breaking encapsulation. We can say that you're not allowed to access these the internals of any of these sort of encapsulated objects, but we can get this sort of reference, which is actually going to be forwarded to this actor. And similarly, we can create a reference which is actually going to a private object here, but it's going to appear as being locked, and meaning that in order to access this thing, we first have to grab a lock, and that's going to be the same lock that we have here. So the same sort of ideas generalized to other modes of concurrency control.
So, why would we want to access the actor through one of its internal objects rather than just going straight to the owner, or the actor itself, if you like?
You should read this paper. But yeah, so that's I had a.
Boy, were you prepared for that question?
Yeah. So
Well, but it answers any questions.
no, but it's a very valid question, and one that and someone who's really into actor systems. I gave a presentation on this thing, and he came to me afterwards, and he said that I like the presentation, but not what you're doing, because the point of having actors is that the things that are private, you shouldn't be able to have to leak those things. Yeah. But the idea is that if you think of this as sort of being the service provider, then as the complexity in here increases, if sort of any additions to the interface has to go via the owning actor. So if we want to make this actor do something more, we have to sort of extend its interface. But with this way, we could sort of abstract this information away and say that this actor doesn't know what the services its internal objects provide, but it's allowed to say that, hey, you take a reference to this thing, and I will perform whatever services it is, but my interface doesn't need to sort of increase in complexity while I'm doing that. It's the one of the ideas. And there are other things, but let's take that offline. So what we have here is a system that guarantees us that since we're following a strict reference capability model, we know that the only way that I could get an alias was if the creation of that alias was safe. So we know that any two aliasing reference capabilities are either composable, meaning that their operations will not interfere. We know that they are synchronized behind a locked or an actor. We know that they are thread local, and they're coming from the same thread. We know that they're encapsulated inside the same aggregate or something. Otherwise, the references would have been, the capabilities would have been forged, and we don't allow that. Yep.
So with regard to the forwarding of messages to locks,
Yeah.
does that make it hard to reason out deadlock for a programmer? Because now, even if you have a well order on the things you're acquiring, it's not guaranteed that we're well ordered by the time you take into account who owns it. So you have to know your owning lock.
Right. So having re-entrant locks helps a lot here. But yeah, it does. I mean, since we're introducing more opportunities for locking, we also introduce more opportunities for deadlocking.
I think it's more of the normal sort of well ordering of locks that you try and enforce. Now you've got, it's not the things you're grabbing it on, it's the thing that they are delegating to. So you have to know what the delegation relationship as well, right? To get like one of your sort of standard ways out of deadlock.
Right, but so I might be wrong, but the idea here is that the lock that you're grabbing is the same lock. That was I'll jump back to here. When you're grabbing a lock on this, you're grabbing this lock, and the only way that you could get to this object normally is if you went via this lock.
Right, but I guess the thing, I now have a reference to something, but it's going to grow a lock on something else.
Is the question really, is it reflected in the type system what lock I'm grabbing or not?
Yeah, kind of, and like, how do I as a programmer know that I'm going to do something,
Yeah.
like, because...
And that is an excellent question.
Okay.
That's all I would say.
Is that going to be the next paper?
Just wait a few slides.
Yeah. No. There are no more surprise papers like this. No, and actually in the we haven't really had to deal with this because the implementation of Encore only uses actors. We haven't had the need for locks because we've been using actors. So deadlock prevention isn't something that we've been looking into. So I should start finishing up. We were here, and the sort of main idea here is that by controlling the aliasing, you're also controlling the concurrency and the effects that are going on. And I'll add a short intermission, and I feel like I should mention Pony, which is another reference capability language that have a fantastic logo, and they're doing very similar things with reference capabilities in an actor setting. And there's a paper here at Uppsala, which is going to be presented on Thursday by Juliana, where this sort of garbage collection type system co-design idea, where they're using the same ideas but for a lot sort of more low-level stuff, and they design a concurrent garbage collection system for actors, which is very neat. So I recommend you go there. So finally, just to recap, while object capabilities specify what you can do with an object, reference capabilities specify what you can do with a reference. And because you know that the whole system strictly follows this reference capability model, you can get global guarantees like encapsulation, thread locality, uniqueness, absence of mutable aliases, and so on and so forth. So finally, to go back, I'd like to think about sort of what's the relationship between reference capabilities and object capabilities. And I think that what I want to propose is that reference capabilities are a complement to object capabilities.
Did you mean E or I? I is very nice, and capabilities say thank you. It means they work well together, but maybe you meant both.
I meant both. So so because they sort of allow specifying how we may share object capabilities further. So we were talking about shallow and transitive capabilities, and that's really an aliasing property. If I can create an alias, which is one that is not permitted to be shared further than I can give to you, and then I know that you're not going to pass it on to anyone else. Or I could give you the permission to create new aliases and pass that on, and that captures something like that. You can say, if you go back to the idea of having thread local capabilities, you can say that here's something which is local, so I know that I can give it to you, and you're not going to do anything concurrent with this thing. So maybe I know that accessing this thing sequentially is safe, and so that I can give you a capability and say that as long as you don't, you're allowed to use this as long as you don't try to do anything in parallel with this thing. So it's about statically capturing best practice patterns, which are like in the e-manual or things like this. You can say that rather than saying make sure that you have a strict encapsulation, you can just ask the type system, this thing is going to be strictly encapsulated, and I want you to smack my fingers if I violate this. You can also think of I mean, a natural question is sort of can object capabilities emulate reference capabilities? So you can imagine that a unique reference is a proxy to a capability, and it has a move operation which creates a copy of itself and immediately revokes the original. So that way you can make sure that there's always only a single capability to the thing. But it's hard to get further than that. I mean, you can imagine doing thread locality by passing in a parameter which is the current thread ID, and you will only be allowed to perform the operation if the thread ID matches, but it sort of gets complicated. So but this way we can with reference capabilities we can do some of these things, but without needing the proxy object. We can let the type system handle the thing statically instead. And there are also other relations which are sort of interesting to explore and that we haven't explored very far. So for example, there's been talking about revocation. I mean, what would it mean to revoke a reference capability? I'm saying that you're allowed to create these aliases, and now you're not allowed to create these kind of aliases anymore. So what does that mean?
To use the alias you had, right?
Right. So what would that mean? And there's maybe some connection to weak references, which is that it's a reference, but it's not strong enough to keep the object alive. So when all strong references have been removed, then the weak reference is no longer there anymore. So there's some sort of connection there, but I don't know what it means really. Yeah. So I'll finish off by just showing you. I really love the mountains on the horizons here in Vancouver, and I just want to show that we do have mountains. They're further away, but we do have mountains in Sweden as well. So thank you very much. I'll take more questions if you have. Yeah.
So I'm in the process of designing a programming language that has some version of, I think, well, I'm calling permissions, but it sounds like it's basically reference capabilities. And I'm trying to do it from a user-centered perspective. And so my goal is to not just design a language that's expressive, but design a language which I can give to people and have them use effectively.
Right.
So I'm wondering what your experience has been with this system. Have you given it to anybody? Have they been able to use it?
So the implementation here is in the Encore language, which it's an open source language, but it was open sourced fairly recently, and sort of we haven't really pushed it a lot. But we have had bachelor students and master students use it too, and sort of also we've sort of used them as the files to sort of clean out some of the unevenness. But I think that it's been working fairly nicely, and one of the points of the kappa type system that I mentioned is to sort of reduce the amount of annotations needed in the code that you write. So the annotations that you see, these linear and local and whatnot, is something that you put in the type declarations, but then you don't need to think about it for the rest of the code. So yeah, it's possible to the main resistance that we've met is the same thing that you were talking about, that the sort of the heavy annotation load is the thing that people don't like when sort of in usability. But it's possible to reduce that enough to sort of when you're defining the class, you have to say something about how this is intended to be used and shared. And once you've done that, the type system take care of the rest.
And how much training do you find you need to give people in order for them to make any progress with the system?
Most of the time, you don't have to be very complicated. I mean, most of the time, things will be thread local, because most data is thread local. When it's not thread local, you have to, they are often immutable, or they are something that you need to. I mean, the most complicated pattern if when you have these linear capabilities that you have to chain through the computation and explicitly pass around. But even then, it hasn't been very hard. But I'd love to show you some code examples and stuff offline that we can look at. I think
So if I understand correctly, this is Rust. There's a little bit of steroids, right? Comment on that.
it's not Rust, but it's doing very similar things to Rust. So the property that Rust is maintaining is that there is at most, I mean, modulo things like these garbage collected, these ARC references and whatnot. There is always at most one mutable reference to something. And this is something that we wanted to, so this works for certain things, but for example, you can't express any fine-grained concurrency, like lock-free data structures is really hard, because the whole point is that you have several threads that are actually mutating the same stuff at the same time.
You can't, I mean, you can't express lock-free data structures unless you can data race.
Right. So there are extra slides that I didn't get into, but we'll. That's what sort of what that would have been about. Sort of the at controlling.
I thought you were trying to prevent this.
Right, but you can. I'll go back to more.
You've got the async, and the async can do anything it wants inside.
Yeah, but still inside the async we're going to use the same model.
No, but it's important to be able to allow races. There are lots of numerical algorithms that are far more efficient if you allow data races.
Right, but currently we don't. We disallow those as well. But you can allow certain data races. So in the things that are on the next 10 slides from here, it's a system from eCoop 2017, which is about saying if we can sort of relax this mutual exclusion idea for certain operations, and by carefully tracking ownership, we can make sure that even though we have like a lock-free list, we can guarantee that whenever you're accessing one of the elements of the list, there can be no data races on that thing, even though there are technically data races on the list itself, because you're doing that. But to get back to your question on Rust, we're trying to allow more concurrency patterns. I mean, Rust is
No, I got it. Yeah.
Yeah.
I think it's really clever. I just wanted to hear your opinion on that.
Yeah, but I mean, I would love to try to explore some of these things in the context of Rust, because I think what Rust is doing is really cool and really important.
And it's really cool for systems people because there is no garbage collection.
Right.
So there's a lot of problems for us.
Mm-hmm.
Could you use the Rust compiler techniques to reduce the amount of annotation you need?
Like tracking lifetimes and whatnot.
Moves and ownership and all that, they do that at the compiler.
Yeah, so really the things that you would use this for is to whenever you're dealing with linear references.
Yeah.
So currently the simple way is to just use destructive reads and say that whenever I move it, I explicitly mark it as a move. But you could use similar techniques as Rust is doing to infer when you need to do moves and not. So similar techniques are definitely applicable. I should hand over to the next. Oh, which is you.